this video, we're going to look at the normal model and when our values are not at specific z-scores like 1, 2, 3, -1, -2, -3. Here's a little helpful table that shows how to sketch a normal curve. You want to remember that when you're sketching normal curves that it should be bell-shaped and symmetric around the mean. The mean should be in the center. And even though the normal model extends forever on either side, we only go out to 3 standard deviations on either side because anything after that has such a low probability or percentage. It's basically 0%. So it's not really worth it to go beyond the 3 standard deviations on either side. Okay, take a second and pause the video and read the problem, and then you can unpause it when you're ready to do the problem together. The SAT test has 2 parts, evidence-based reading and writing and math. Each part has a distribution of scores that's roughly unimodal and symmetric and is designed to have an overall mean of about 500 and a standard deviation of 100 for all test takers. In any one year, the mean and standard deviation may differ from these target values by a small amount, but they're a good overall approximation. Suppose you earned a 600 on one part of your SAT. Where do you stand among all students who took the test? And you want to remember to think, show, and tell. Okay, so we want to think about what this problem is asking us for, like what am I looking for? And I'm pretending that I'm that person that scored the 600 on one part of the SAT. So where would I stand among everyone else who took that test? Okay, now to show that, I have my sketch of my normal model, and I know it's normal because it says that the distribution of scores is roughly unimodal and symmetric. So I can apply the normal model, and I want to calculate now some things. So the first thing I want to find is, what is my z-score if I'm scoring a 600 on the SAT? And remember, your z-score is just your value minus the mean divided by the standard deviation. So my value is 600. And I know the mean is 500 and the standard deviation is 100. So that gives me 1. So what I want to know is the probability of z being less than 1. Okay, so if I'm right here at 1, that's me, okay, where do I stand? So I want to know, in other words, like what percentile am I going to be? Okay, so we know from the past that this represents 84%. So how are we getting that again? Remember that it's 68% of the distribution falls within 1 standard deviation of the mean, and a property that the normal model has, it's symmetric. So 68 divided by 2 is 34. So this is 34%, and then this is 50%. So I've just got my 50% plus my 34%, which gives me 84%. Okay, so what does that tell me? It tells me that if I scored a 600, that I'm actually in the 84th percentile. Okay, and what does that exactly mean? It means that I scored higher than about 84% of all students who took that test, that same exact test. Okay. When the value doesn't fall exactly 1, 2, or 3 standard deviations from the mean, we can look it up in a table, and it's called a table of normal percentiles. And it's also known as a z-table. And I provided you the z-table in the Canvas modules. We can also use technology, which is much easier. So I'll show you both ways. So below is a histogram of the heights of all Major League Baseball's pitchers at the start of the 2017 season. The mean height of the pitchers is about 74.5 inches, and the standard deviation is about 2.1 inches. I want to know what proportion of baseball pitchers should we expect to be at least 78 inches tall. So the first thing I need to do is find the z-score for the pitcher that's 78 inches tall. So I'm just going to subtract 78 minus the mean, 74.5, and I'm going to divide by the standard deviation, 2.1. And when I subtract the numerator, I get 3.5 divided by 2.1. So that gives me a z-score of 1.67. So that's not exactly 1, right? So I can't use my 68, 95, 99.7 rule. So I'm right about maybe here. Okay, that's where that picture would stand in comparison to everyone else. So if I want to know what proportion should we expect to be at least that tall, at least means that or more. So I'm looking for the area to the right of the 1.67. In other words, I'm looking for the probability that z will be greater than 1.67. Okay, so what I need to do now, I'm going to show you both ways. One way to how to find it on the calculator, and the other way is how to use the table of normal percentiles, or the z-table. So if you go to your calculator, okay, the first thing we need to do is go to what's called normal CDF. So to do that, I need to hit second vars, and then normal CDF stands for normal cumulative density function. That's number 2. So you're gonna either click number 2 or arrow down to it. And it's gonna ask you for the lower bound, the upper bound, the mean, and the standard deviation, okay? So what I need to do, if I look at my graph, my lower boundary would be 1.67. Remember, the graph goes on forever towards positive infinity. We can't type infinity down for our upper bounds, but we can use just a really big number, like a really big z-score. So we can type in like 10,000, okay? That's basically 0. So 1.67 is my lower bound. I think it's gonna make me type it in again. So second vars, number 2. Okay, so 1.67, and then you want to hit the comma. The comma is underneath the sign button, S-I-N, and then your upper bound would be 10,000. And then the mean, it's a standard normal distribution. So my mean is 0, my standard deviation is 1. And then all I need to do is hit enter. And I get 0.0475. So that's the percentage of baseball pitchers that would be taller than someone that's 78 inches tall, okay? So that comes out to be, let's write this out now. We have normal CDF, my lower bound was 1.67, my upper bound was just 10,000, my mean is 0, and my standard deviation is 1, okay? So you can see the mean is 0, and then the standard deviation is 1. And we got 0.047 approximately, which is basically 4.7%. So what that means is, this is the tell part, about 4.7% of major league pitchers should be at least 78 inches tall. That's the probability that you would find a major league pitcher that's taller than 78 inches. Feel free to pause the video and read the next problem and try it on your own, and then when you're ready, we can unpause and do it together. Suppose a college says it admits only people with SAT verbal scores among the top 10%. How high a score does it take to be eligible? So this time they're giving us the percentage. We need to work backwards. So let's first draw a picture and kind of figure out what's going on here. So again, I know that the average SAT score is 500. So that's going to go in the center, right? That has a z-score of 0. And then we're going to add 100. That's the standard deviation. We're going to go out 3 places to the right, subtract 100, go 3 places to the left. Okay, so now I'm 3 standard deviations in either direction. So if I want to be in the top 10%, where is that? Where would I draw my flag? So what I need to do is I need to utilize a different command on the calculator, and it's called inverse norm. Okay, and it's in the same place you get normal CDF. So the thing is, I need to figure out top 10%. If you're thinking of top 10%, you're not going to be down here at 10%. You're going to be up here. So what would be the area to the left of that? That's going to be 90%. And I'm getting that because it's 100% minus 10%. So that means I'm looking for like, okay, where approximately is the area under the curve 90% or 0.9? The area under that curve, the one we just did, was 0.047, okay, or 4.7%. So what I need to do is go to my calculator, and I'm going to go to second vars, and this time I'm picking number 3, inverse norm. And we type in the area, which is 0.9. Okay, now remember, if they said bottom 10% or lowest 10%, then you would actually type in 0.1. But since it's the top 10%, you're in the 90th percentile. And then my mean is going to stay 0. And let me do that again. Second vars, number 3. So it's 0.9, comma, 0, comma, and then standard deviation is 1. And then hit enter, and you get 1.28. That's your z-score. So it was 0.9, 0, and 1. And we got 1.28. So that's the z-score. So what I need to do now is use my z-score to work backwards. And I'm missing this, right? That's what I need to find, is the score that would make it eligible. So I'm just going to plug in. I know my z is 1.28. I'm looking for y. I know that the mean SAT score is 500, standard deviation of 100. So now I just need to solve that. So to solve, what I'm going to do is I'm going to get y by itself. I'm going to multiply both sides by 100. And I would be, in order to cancel out those hundreds, I would be left with 128 equals y minus 500. And then to get the y by itself, I would need to add 500 to both sides, and you would get 628. So what that means is 628 is the cutoff for the top 10%. Okay, right here, I'm at about 1.28 standard deviations above the mean. And that person, the cutoff score, would be 628. Okay, please feel free to pause the video and then unpause it when you're ready after you've read this next problem, which has several parts. A cereal manufacturer has a machine that fills the boxes. Boxes are labeled 16 ounces, so that the company wants to have that much cereal in each box. But because no packaging process is perfect, there will be minor variations. If the machine is set at exactly 16 ounces and the normal model applies, then about half of the boxes will be underweight, making consumers unhappy and exposing the company to bad publicity and possible lawsuits. To prevent underweight boxes, the manufacturer has to set the mean a little higher than 16.0 ounces. Based on its experience with the packaging machine, the company believes that the amount of cereal in the boxes fits a normal model with the standard deviation of 0.2 ounces. The manufacturer decides to set the machine to put an average of 16.3 ounces in each box. What fraction of the boxes will be underweight? Okay. So the very first thing I need to do is find z. And I need the weight of the box, which it says it's 16 ounces. And I need to subtract the average weight, which we know is 16.3 ounces, and divide by the standard deviation of the weights, which is 0.2. And when you do that, you get negative 1.5. So that means I'm 1.5 standard deviations below average, okay? What fraction of the boxes will be underweight? Well, underweight would be these guys. So I'm looking at the left. I'm looking at the probability that z will be less than negative 1.5. Okay, so remember, to do this, I need to use my calculator. But let me show you another way to get the same answer. So if you go into Canvas and you go to our class in the modules, you can see that I provided under stat tables the z table. So I'm going to take that and I'm going to place it in Notability so that I can write on it. Okay, so we had a z-score of negative 1.5. There's going to be 2 pages to this. This is where your z is negative. This is where z is positive. So since z is negative, I'm going to add in a 0 there, okay? I get negative 1.50. So this negative 1.5 is the row that you're going to look at. Okay, so I'm going to look at negative 1.5 right here. And then this last number is the column that I'm going to look at. So I'm going to look at this column, the 0 column right there. And where they intersect at, as long as I'm looking at the left, which is what the table is kind of designed to look at, as you can see it's shaded on the left, so that's its default, the area or the probability would just be 0.0668. If I am looking at the right of where the flag is, where z is, I would need to subtract this number from 1 because the table is always defaulted to shade on the left. Okay, for this table. There's other types of z tables you can find all over, but this is the one that you have access to. You're welcome to learn how to read the other ones, but this one is just to the left of z. So we know our answer is 0.0668. But what I'm going to do is I'm going to use technology, okay? And we'll compare our answer. So remember, we want to do normal CDF. My lower bound this time, lower boundary would be down here. So that's going to be negative infinity, but we can't type that in. We're just going to put negative 10,000. My upper boundary is negative 1.5. And then my mean is 0 and my standard deviation is 1. So when I type that in now, let's see what we get. So second, vars, number 2, normal CDF. We gotta wait for this. And I apologize, this will be over soon, hopefully. There we go, okay. So normal CDF, we've got negative 10,000 and then a comma and negative 1.5 comma 0 comma 1 and then hit enter and you get the same answer that we found on the table, 0.0668. So what that means is, if we were to write that out in words, about 6.68% of the boxes will contain less than 16 ounces of cereal. And that's the end of this video. We're going to pick up with the next one with a problem that relates back to the one we just did to give you a little refresher and review before we finish up. Have a great day, everyone.